Go. So welcome everyone. So this is somewhat light-hearted talk about threat modeling. We'll describe the talk in a little bit more detail in a moment. Firstly, a little bit about us. My name is Andrew Lee Thorp, and this is David Johannson. So I regard myself as a sort of expert cynic, which is a slight character flaw, but is otherwise kind of useful for threat modeling, which is one of the things I do a lot at Synopsys, amongst other things.
Hello. Yep, hopefully it's on. I'm David Johannson, working as Synopsys as well, with my colleague Andrew. Still working on the part of being an expert and a cynic as well, but I'm getting there slowly. So we do a lot of different types of work, and we both worked in industry for more than 10 years and done a fair bit of threat modeling. The purpose here of this talk is to share a bit of some stories and some experience we had and things we come across that some of it may be obvious, others issues may not be obvious at a first glance. So just trying to share some lessons learned from that.
So what is threat modeling? On a high level, it's building a model, a representation of the system, of a real system, of a complex system, and you can never condense a complex system into a two-dimensional model or even a three-dimensional model. It's more than the sum of its parts, and they're usually complex. So it's building a model, and then it's asking questions about the system using the model. So interrogating the model. This is the creative part. This is the analysis part. And finally, we're not doing threat modeling unless we find some real threats and we want to fix them. So part of the threat modeling process is identifying how to fix the defects that you find. So the process is important. Theory is good, but we're not here to talk about the theory. There are lots of good talks on theory. And you should clearly follow the theory, but we wanted to have a little bit more fun to show you what sort of things we find in practice, a little bit about how we got there. But so this talk is about threat modeling and design flaws.
So what's the design flaw then? So if you look at the picture here, what do you see? Yeah, something that doesn't look quite right. So this is actually a picture from my home, my new flat back in London. And somehow the builders managed to build the boxes housing my router in such a way that you can't actually open the door. It's stuck on both ends, so to say. So it's a little bit of a usability issue. If I need to change any cable, so that it's a bit difficult to get into and fix. And it's basically a poor quality issue, right? So it's something that has an impact on the use. May not be a security issue per se, but it's a quality issue at least here. If we look at another example of a design flaw, some of you probably have seen this one. It's been around for quite some while, but it's quite telling. I think this is one of the most telling stories of what threat modeling is about, right? It's not only about breaking a control and looking whether there is a control, but other ways around it. And we can see here there's a design flaw in terms of they had a control, and even though the control might have been perfectly implemented and very secure there are very easy ways around it. And we can see as soon as the first snow starts to fall that you can quite easily get around this, and we see that that's actually what's happening. So it's pointing both to a design flaw here, but also to a very common attack pattern that we always should try to evaluate when we are doing threat modeling, whether you can bypass a control. So that's what we mean by design flaw. So what we're going to do now is look at, I think, 6 different examples, and we're going to see some design flaws we encountered in actual real-life system. Obviously, these have been changed a little bit and they're fully anonymized, but these are not just made-up things. These are actual things that are based on applications we come across. So the first one is about who sent the message, and it's about a system that on the surface had very good security controls and looked to be very secure, but in reality, it was actually really hard to tell who sent the message in the system. So if you look at it first, we see that it was a a classic type of system with various different tiers. And we had a client that was connecting to a perimeter system first, where they had on a transport layer mutual TLS. So it was a very strong form of authentication of the client. In addition to that, they also had the message layer using XML signature. So it was a business-to-business application where they were sending web service requests with XML messages that had been signed by the client. So both on transport layer and at the message layer, they were having security controls. In addition to this, they also followed best practice in terms of auditing events and logging when messages were sent. So they had an audit trail of that, and the avoided storage on the same system. So they were sending it off to a secure log server, where they both had signatures of the logs to prevent manipulation of them and also encryption of the logs. So when you look at this, it looks really, really strong. And normally in a quick threat model, we'll see, okay, you have these controls and everything looks fine. So what could possibly go wrong here? Anyone with any ideas? Yes?
Reverse proxy is follow the information.
Yeah. So you're on the right track here. What we see here is that the controls themselves were strong, but the integration here was flawed. And one example is with reverse proxy, you mentioned the authentication here on the transport layer had no correlation whatsoever with the signature verification on the message layer. So they did not check that the same entity that had authenticated was the same entity that actually had signed the transaction. So those could be two different entities altogether. And to make it worse, when they were actually then logging who had sent this message in the audit log, they were taking the sender from a field in the actual payload rather than the authenticated session. So in other words, you didn't know who actually sent the message because you could tell whoever you wanted to be. So in practice here, these controls that by themselves were quite secure and well designed, so to say, in reality did not provide security that they had anticipated here because they had not been integrated properly. So what this means is that when we were looking into this and asked them like, okay, so who actually sent this message? What does your log say? You couldn't really tell because a client could connect to the system as client A, for example, where the one certificate and be identified by the proxy as being client A. But the message itself then could have been signed by a completely different entity, a completely different company, client B, let's say. And then if you then went to the audit log and had a look in there, it would say the message was sent from client C, which has no relation with the authentication or the signature. So all these controls were actually not giving them the assurance they wanted. So you couldn't tell who actually had sent the message here. So what do we learn from this? Well, I think one of the main points here is that having good security controls is not enough by itself. It does not automatically mean you have a secure system. So when you design or review a system, you also need to check that the controls that are employed are actually working together and they are collaborating, so to say, and enforcing the same picture of who the user is, for example. You need to make sure that they support each other when you have different controls implemented at different layers. Another point here is that also when you have any type of information in an audit log, it's not only about securing the log itself and making sure the information can't be tampered with or read by unauthorized users. You also, of course, need to check what is the source of truth? Where does that information come from? Can that be manipulated by a user or is it taken from the right place? For example, it should have been taken from authenticated context rather than from a data field in a message. Okay.
Good. Okay, so the next example we're calling mind the gap, stepping over the step up, right? So imagine you have a system that does step up authentication. Let's just go through. So we have a few layers which you've just simplified slightly. You go over the internet. You get like an auth-in layer. Maybe there's access control checks as well. Ultimately, you have a backend. So we've simplified this slightly, but the essence of the problem is described in this diagram. And you have a trader. He wants to do something risky. He wants to trade a few K. So he sends a message. I want to sell 10,000 shares. So what's going to happen? Well, there's a session. So the authentication layer is going to say, yeah, this is a valid session. Bob's a trader. I'm going to forward this to the business layer. Goes to the business layer. And typically what you have is some kind of risk engine. Say, Bob wants to trade 10K. I'm going to go through a risk process. And it's going to say, well, this is risky. I'm not happy that you've just done single factor. I want you to step up. I want you to prove that you're really Bob, because this is business-wise, it's a risky transaction. So the server will say, okay, you need to step up, sends a challenge, some kind of out-of-bound challenge, or it could be in the app itself. Doesn't really matter how it's done. And is going to be expecting a valid response. And the response comes back. And there's some validation taking place. You got an OTP, some assigned some kind of response, like a challenge response thing. That's going to go through a check. Is this a valid response to this challenge? Yeah, it's okay. And it's going to invalidate the OTP. Typically, issue a new session. I'm happy. Send it to the backend, and the backend can then go and execute the transaction. That's sort of the general flow. So and then we're happy. We do the transaction. And that's just the happy world scenario. So let's try to think about how we can attack the system. Let's start to think about this. So we get all the cookie cutter attacks, all the standard attacks, though, out of the box attacks. We could attack the device or even the user. There are a number of ways you could do that. You could try and get a bit of malware on the device. You could try and get something on the device through compromising a CDN. So this is the kind of the man in the browser, man in the app attack. And this would be a valid attack, quite a sophisticated attack. It's not really attacking the step up, but it's certainly a valid attack. If you could do that, you could inject your own transactions into the stream, into an authenticated session. But we want to see if we can attack the step up, because such an attack would allow you to do other things. So you could attack the channel. If it's HTTPS, a little bit difficult to do. Maybe they're not doing certificate pinning, but that's a standard cookie cutter attack. Maybe you could attack the risk engine itself. Maybe we could trick the risk engine into not doing this step up. That would start to become a little bit more of a creative kind of attack. That would be quite difficult to do from a threat model, because then we really need to understand the details of the risk engine in order to trick the risk engine into not stepping up. But it's a candidate. But what we've got so far is we've got this two-dimensional model, and we're thinking about poking the system in all these different places. And we can apply sort of these standard stride type attacks of the different attack surfaces. But what we need to remember is we need to think a bit. What else could we do? So what we need to remember is when we're looking at these threat model diagrams, we're seeing this two-dimensional model, maybe three-dimensional if you take into account the tech stack. But the systems also have a time dimension. There's a sequence diagram. There's a state machine. There's a state machine in every tier, and there's a state machine in the system as a whole. And if that state machine is not coherent, then maybe you can attack the state machine without attacking the attack surfaces directly. So let's look at the state machine. So the first thing is, if we just recast the previous diagram as a state machine, we can just go through the sequence diagram. You log in, you get a session, you try to do a transaction. It says, that's too risky. Do the step up. You get a challenge. You get a response. Then you get the checking of the response, a new session token, which gets sent back to the client. And eventually, that's the next thing. And then eventually they can go ahead and do the transaction. So if we look at a sequence diagram of this thing, it's just simplified slightly. We have the same thing. We start, we're signing in, we're signed in. That's the password part. And then we need to do the step up. So we're in the stepping up state. We're verifying the challenge. We're issuing a new session because it's a risky transaction. And then finally, we're in the stepped up state and we continue. So let's take a moment to think of what does the attacker have? Sometimes it's useful because that opens up new attack possibilities. Well, the attacker has his own session if he's an authenticated attacker. If he's a malicious attacker, a legitimate user on the system and wants to attack other people, they have their session 1 for the password, session 2 for the step up. So we can, what does that give us? Could we maybe step over the step up, so to speak, and just skip the entire state machine? And the answer is, well, maybe. Yes, maybe if a few other conditions hold. And one of those things is that if the attacker knows the victim user's password, then maybe if those sessions are not correlated, then maybe they can log in as the user, then substitute their own step-up session token and do risky transactions as the victim user. Now, that's an attack possibility. In fact, that happens more often than you think. So let's go to so the attack works like this. The user logs in, the attacker logs in as himself, collects his step-up session token, then he logs in as a victim user, substitutes his step-up session token, and submits it along with a risky transaction that is tantamount to a risky request. And so he executes the transaction. What you need to realize is often in the new world of service-oriented architecture and microservices, there are many services and they each have a single responsibility. So there's a password service and there's a step-up service and there's the business service. And because they have a single responsibility, there's no one component that has a responsibility for the system-wide invariant, which is this token, password token, the same as the step-up token? Because it's not part of the architecture. So that falls through and it goes to the business layer. The business layer has a choice. Who's the user? And typically, in a lot of systems, this kind of thing has been bolted on afterwards. And the way the change is done, changes are done to minimize impact on the rest of the system. So typically, when we look at a system like this, the original business layer looks at session 1 and it doesn't look at session 2. And there's no coherent enforcement of the fact that these should actually belong to the same user. So effectively, we've stepped over the step up. We go to the next one. So what can we learn from this one? So I would say don't take controls at face value. If someone told you they did a step up, they used OTP, it was signed, they send you a challenge, it was signed, and that's a one-time password, don't take that at face value. The other thing is sometimes if you just think locally, it gives you some ideas about a new attack possibility. If we just think, what can this attacker do? Then sometimes that can open up new attack possibilities, because your traditional alternative is sort of an attack tree, which is a top-down approach. Sometimes you take a bottom-up approach and it gives you new possibilities. And the other thing is, when you do threat modeling, don't forget to attack the state model.
Okay, yeah. So the next example we're going to look at is about secure password storage. And unfortunately, in this case, it had a little bit of unintended insecure side effects, and you will soon see why. So it all started with a classic company, probably been around for a long time. And back in the days, people were not really aware of securing passwords, and they were often stored in clear text, and they happened to be one of them. And as security became more important, they had an application security group, and the security department got hold of this and realized that this is something we need to address. So they tasked the team with fixing this by removing all the clear text passwords and make sure they were securely hashed. So they had done a really good job actually in reviewing modern standards and latest recommendations in terms of password hashing and using adaptive hashes and unique salts and all of that thing. So they had implemented that, and they had now secure password storage with using adaptive hashing with sensible parameters and unique salts, and everything looked fine. So the security department was quite happy and said, okay, problem solved, is fixed. Well, it was fixed for a while until the fraud department called and said, our fraud detection algorithms don't really work the way they used to work before, and we're missing some parameters here. We used to look at the password of the user when we were doing the calculations in terms of fraud, because apparently some common passwords used by fraudsters is part of the calculations in the system. So they needed the user's password. And before, they could simply do that by just do a lookup of the user in the database, right? And they would have the password. Now, with the hash passwords, it didn't really work the same way because the algorithms were used to having a clear text password. So they called the developers and asked, can you fix this for us? Can you help us? And of course, developers came to the rescue. So what did they do? Well, wait a minute. The user needs to buy something. So they are logged in. And when they buy something, they need a password. So we can't take the password from database anymore. But wait, what if we just store it in the session when the user logs in? It's just temporary, just in the session in memory for a little while until they buy something. And then we eradicate it. It's all fine, right? So they had it in the session and passed it along with the purchase to the fraud engine. So the fraud department was happy. They could do their checks and everything seemed fine. And what I didn't think about when I had a look at this was that, of course, in the production environment, it was not just one server, and they had multiple web servers in a web farm, and they were all using a SQL server kind of like state database for the sessions, right? So what does that mean? Well, the password that they thought was only in memory in the session for a little while was actually persisted to disk in the DMZ in clear text. So moving from the database that was in their internal network, a bit more secure than clear text, they actually moved the clear text passwords out to the DMZ in a different way. So good intentions ended up with not so good results. So the lesson from this is, as we are fixing some things, we may end up creating another problem. So what it means, we can't only look at the immediate fix and the initial threat model. When important things changes, especially anything relating to security controls such as authentication or authorization, you should always revisit that threat model. Threat model the new iteration. Don't just threat model the initial thing when they change something, but also go back and ask them, how did you change that? What was the implication? And did you do any additional changes from what you told us you were going to do initially? So this is not always easy to catch unless you go back and verify this and try to get some evidence of how things were changed. Because the full impact of these changes are not always well understood up front. And it may be only after they have been done that you can actually see the full impact of the change. So another thing here to point out is that the deployment scenario, right, that also has an impact on the security. Some of the assumptions you make during the initial design and development may not hold true in the environment where your software is deployed. So while security threat modeling is often focused on the software itself when it comes to application threat model, but I don't think we can discard the deployment scenario completely because that also impacts the security. Just like the first keynote today, we talked about, even if you have the perfect software without bugs, the hardware it runs on can sometimes be abused to cause issues and vulnerabilities. So we need to look at the full stack. We need to consider the full system to get a better picture. The next one is about one-time passwords, but in parallel universes. So what does this mean? Well, let's look at this. There was a company that, as many others, wanted to support remote workers. And as you know, your employer might not be fully comfortable with you logging into their company systems just with your AD credentials, for example, remotely. Probably they might need a little bit more security. Oftentimes they want to add a second factor and, for example, use OTP, like a time-based OTP or a similar system. So this is what they had done. Looked at this and it looked fine. They had a password as well as an OTP that was provided to the system. They were validating the credential against their LDAP directory, for example, and then they were checking the OTP to make sure that it was a valid OTP value. And of course, one of the points with this, right, is that if the user would be on a system that was monitored by a malicious actor or someone who was able to get into the network layer and capture the credentials somehow, they should not be able to just replay those and then log in directly to the system. So if an attacker was trying to replay this credential, while the password was right, the OTP should have been marked as already used right. So they would not be able to log in. So the system would set stop for that and prevent attacker from replaying the credentials. So far, so good. Everything seemed fine. Until you realize that this was a rather large company with employees all over the world. And of course, it was not enough just to deploy this on a single system. So they needed it on multiple systems in different regions, and it was load balanced. And could that potentially impact things? Well, we discovered that after some evaluations and testing with them, we found that we were actually able to replay this. So how did that happen? Well, when the user logs in, it goes to load balancer, which sends it to one of the instances, validates the credentials, and marks the OTP as used after it has been validated. So far, so good. But if an attacker is now capturing these credentials, replaying them, and happen to be redirected to another instance, what do you think happens? Actually, the OTP was now accepted. And we were able to replay credentials and log into the system, although it was supposed to be a one-time password. And the reason for this was they did not have proper syncing between their systems. So although it was a one-time password, is only in one universe, as I said. So they had multiple instances. So you need to make sure that you have the same picture of the state in all of your system. Again, you can't only review it in one instance, but you need to look at the whole system to try to discover these things. So synchronization is really important here, not only of the OTP itself that is within the time frame, but also when it's marked as being used between systems, if you have more than one instance. So just like I said before, you need to consider deployment scenario as well. It can impact the security, and what is secure in a single deployment environment on just one instance may not be secure when you deploy to multiple instances in a load balance fashion. So you need to take that into account as well, both when you design and when you review the security of a system. And just like in threat modeling, these can be harder things to find. I also know from doing a lot of security testing in practical penetration tests is similar. It's also quite hard sometimes to discover these issues because you're getting results that are not consistent, right? As a tester, we want it to be predictable. You send something, you get a result back, and you can review that and make conclusions based on the results. But if you're getting like what seems to be random successes with an attack, and sometimes it fails, they can cause make it very hard to determine what's actually happening. So these are not always easy to find in tests. So you need to know what kind of deployment environment you're working with to try to determine whether that can have an impact on the results you're getting from your tests as well.
Okay, so the next story we've called Secure Connection or Open Door. So this concerns the design of tracking solutions, and they sort of work the same way. And tracking solutions obviously has a lot of use cases. Vehicle fleets, elderly people, pets, loved ones, anything valuable. So they all kind of more or less work the same way. And we've abstracted this, but this is based on real system. So the first thing is you need, in these kind of systems, they have ability to know where they are. And then they report back the data. In this example, they're reporting back the data over a 2G network, could be 3G network, over a GSM network. So they connect to you. What typically happens is you get issued a SIM card, and the SIM card is locked down to an access point name. And when you make the connection, you say, I want this access point name, XYZ. And what's going to happen is the mobile network operator is going to set up a connection to some endpoint where the hosting company receives the data. And typically that also creates some kind of secure tunnel. And typically these things are using sockets. So under the hood, they're using the Internet Protocol, TCP. And there's also a web interface usually for people to manage the system or view their own behavior. So there are different ways to interact with the system. This is more or less how they work. So let's think about attacking the system. How could I attack it? So I can roll out the standard attacks, and those are valid. So let's have a few ways. We could try and attack the tunnel itself. We could attack the web, attack the web app. That's the usual or try and get in through the web app, find a vulnerability, attack the back end. We could be a malicious insider who could steal the data. We could try and attack the tunnel itself. That would be a little bit difficult. This is the standard attack surface. So we can be a little bit more creative than that, because that's not that interesting. So anything else? Can anyone think of any other ways to attack the system? Sorry? APN. So you would attack the network operator? That could be a valid attack. Any other ideas? Sorry? So what, like spoof coordinates maybe? You could spoof. Well, you're in control of the device. You can completely lie about your coordinates. Yes. Yeah. Yeah. I mean, yes. Okay. So you could also spoof someone else's coordinates. You could lie if the system wasn't. You could pretend to be someone else's vehicle. That could be an attack. So those are all valid attacks. Let's think a bit more. What if you were a malicious user with a SIM card? Well, what you could do is you could send messages to people on the same network, and you could say, hey, configure yourself like this, or download your firmware from over here. Because ultimately these command messages are text messages, and you have to have a SIM card on that network to receive it. So that could be one way. Anything else? I mean, now that we're thinking about the malicious user, any other ideas? So let's go back and give you a hint. So sometimes it just stands out of the blue because just the way the system is defined. So next one. So there's no DNS and there's IP. So how are you connecting to the back end? Over IP, over the tunnel. It's there. It's ready-made for you. You have a connection to the data collection server. So maybe if we go to the next one, I can just use my privileged position to attack the data server. Now this could be a clue to something else you could do. What would be a question you would ask at this point? And the question we asked is on the screen. Show me your firewall rules, please. And once we had a look at those, boom, we had an open door. If we go to the so we could use the SIM card to attack the data center, because everything's IP. We can just try and scan the data center, find valid servers, and then try and attack them through this privileged position conferred by the fact that we had a SIM card with a secure tunnel straight into the data center. So what can we learn from this? So actually, this is an instance of a well-known attack pattern, which is create a malicious client. So it's to create a malicious client, and we have a definition there on the screen, so you create a malicious client and you abuse the assumptions made in the design, which aren't, even though the concept is completely straightforward, it's sometimes useful to think about what the attacker can do to get there. So the other thing is you have controls on many layers of the stack. You got, the application layer and the transport layers, and these all have to work together. So the control preventing an attacker attacking the system was a layer 3 control. So we mentioned this already. When threat modeling, think about the tech stack. How does each layer support the solution? Because this is the existence of weak firewall rules was critical. And I think there we go. Yeah. Is this my one or your one? Okay. So I think this is our last example, is username. And we just wanted to use it as a way of talking about assets. Is a username an asset? So what is an asset? We typically think of assets as being data, but they could also be functionality, something about the system. So an example could be subscription for your broadband provider. So just the access to the network is an asset, because users who haven't signed up shouldn't have access to the network. So your download upload speed that you signed up for in your contract, that could be an asset. Or your monthly allowance could be an asset. In reality, assets are not the end game. They're just one way of discovering attacker goals. So if we can think of it as enumerating the assets, it's kind of a bottom-up approach. We can find all the assets in the system, and maybe we can think about new attack goals. Whereas attack tree is something a little bit different. We're starting at the top, and we're thinking about an attack goal, and we're doing some kind of decomposition. I want to read the CISO's email. Well, I can do it this way, or I can sit next to the CISO on the way home on the train. It's just a bottom-up way of deriving attack goals. So is user ID an asset? What do you think? Depends, right? So the example we have is from a multiplayer game where critically there was money involved. And so people were playing for points, and there was a leaderboard, and there was money for the best player. So what's the attack here? Very straightforward attack. Yeah. Find out who your competitors are and just DOS them. And so you just log in as these identifiers, as these users. You have their IDs. Just try some bad login attempts, and you can lock them out. Do we move on? So there we go. So this really happened. And of course, the help desk soon got lots of calls from extremely irate users who were near the top of the leaderboard, and they were complaining about they were busy playing and suddenly they got locked out of the game. And in this way, Bob can simply climb the leaderboard. Now, so we see other examples of where another example of where a user ID is an asset is when in consumer to business or business to business. Typically, the requirement for business to business is high availability. In that case, something like an access key identifier could also be an asset. So what are the lessons learned from this one? Well, in some cases, again, an identifier could be an asset, but also asset discovery, it's a bottom-up technique, can help you think about new attacks. Not all users are equal. In the case, for example, of a business-to-business system or consumer-to-business, those user identifiers have different security requirements. So, in fact, this is a violation, if we just abstract it a little bit more, just a violation of a well-known design policy, which is the policy of least common mechanism. In this case, in the case of business user identifiers, that's sharing the same namespace with users.
Okay. Yeah, so what we've seen here, hopefully, is just some examples for you to take away as either if you're performing threat models, things to keep in mind in terms of looking at both the software, technology stack, as well as the deployment infrastructure. And also, if you're a developer or architect designing systems, some of these things may be things you can keep in mind and see if there are similarities or similar pitfalls that you could potentially fall for and try to avoid them. So the thing here is that these things do exist. We often talk about threat modeling, and there's a lot of talks about processes and all of that. What we want to do here is talk about some actual things that we encountered and what kind of design flaws there are out there, because they do exist, and some of this becomes very theoretical, but hopefully we showed you some examples of how these design flaws come into effect in various systems. And one of the things we want to point out is that threat modeling is often focused on controls and ways where controls are missing or can be bypassed. And that is a really good starting point. And often we should have like checklists or similar things of standard mitigations and things your system needs to do to protect various things in terms of good design, but the controls themselves may not be enough to review in isolation. You need to look at the whole system, how these controls interact, how they support each other, and how they build up the security of the system to make sure that they actually provide the confidentiality, integrity, and other security properties that you want of your system. And with that, we want to say that threat modeling is something that you can use to try to uncover these issues and help you identify these risks and hopefully fix them before the bad guys do. And with that, we're running out of time. I just want to say keep calm and carry on threat modeling. And hopefully you got something with you from this session. If we have a few minutes, maybe we can take some questions.
Okay, we can take 1 or 2 questions for this session. But first, let's thank the speakers. Any question? Maybe let's take off with one question. You're referring to the threat modeling as a way to actually identify some of the issues. I can imagine, depending on how you actually execute your threat modeling, some of the issues might actually end up being enumerated, others might not. Do you have some good suggestions to say, well, if you start with Stride or anything else, what are the things that you need to add on top of that to identify more issues than you normally would do with your team?
Yeah, so as I said in summary, what I think you can start with is if you have like a standard checklist may be good to compare against, and there are standard methodologies like Stride, for example, looking at spoofing, tampering, repudiation, and those type of threats to help you think about whether there are any threats related to those kind of categories that can apply to the system. But then I think there's also there are the standard ones that you can use, but I think you need to build for the vertical you're in or technology stack you're in. There are specific things both to the industry and to the technology that is used that you also need to consider. So I think you can look at the various things that come from not only from Stride, but if you look at testing standards, for example, you can look at things that people would look for in a penetration test, and you can see and try to think of, are those pointing to issues that could be design flaws that you can also try to consider in the design phase. So there's a combination of material you can use to try to cover that.
I was also thinking about deployment views, for instance, because some of the issues you found were not only on the architecture basis, but also the way they were deployed, for instance, the way you actually distribute, the way you actually duplicate certain services. Is that something that you already need to put forward then, or?
Yes, good point. So actually what we do in, there are various different threat model methodologies, but one that we use at Synopsys is actually overlaying a component diagram onto the deployment as well. So we're looking at how these systems are deployed and in terms of the infrastructure and the service and so on. So we're not only looking at the logical flow of data between components, but also how it's actually deployed in infrastructure wise.
Okay, thank you. Any other question?
Yep.
Hi, name is Yami. So correct me if I'm wrong. It seems to me the value you get from threat modeling is a function of the individuals or the parties involved in threat modeling's exposure, and understanding or context understanding of the system that is being threat modeled. Can you speak about maybe some resource or some maybe some community or something where there's like a guideline of things you should consider when reviewing this type of system or something like that? I'm not sure exactly what it is, but I'm just saying maybe there's some resource out there, maybe from a community perspective or from maybe research work that's been published out there that you can recommend or say, if you're doing threat modeling for this particular use case, we would recommend you check out this or be part of this, something like that.
Yeah, good question. So there are some initiatives that are trying to help with that. I know there is an OWASP initiative working on example threat models. I haven't reviewed it myself personally. I'm not sure how much material there is there yet, but it is an initiative about gathering examples of threat models for various systems and have that as like a template or a guide for other people to look at and try to help them think of what are the types of threats and things they could apply to my system that is similar to this. I know there's also some for various industries like automotive and medical systems and others that have published some threat models, both from companies like ARM, for example, and I think AWS has published some threat models and similar. So I think those are the ones we can look at to help you get started. Talking about OWASP, I think there's also a Slack channel for threat modeling within OWASP. I've not been involved myself there yet, but I know there's a quite large community and a big group there, so that could also be a good resource to ask questions and get some help from the community.
Yeah, I'll just add one or two things. There's also the concept of archetypes. Just as there are design patterns, there are design anti-patterns, and they typically manifest themselves in types of systems. So a distributed system has these common kinds of problems. Mobile apps, there's some common themes, some common strands when you come to these systems. So you can look at the architectural pattern and reel off a checklist of attacks that apply to that kind of system. So a client server system, maybe it's likely to have business logic in the client. So you can apply patterns to systems, not just looking at the interactions discretely.
Thank you.